Hello everyone, Happy New Year. Hope everyone has had a good December, winter, festive holiday break, whatever you call it, and you are well prepared and fresh for the new year. This is of course 2024, and in the Math Olympiad world, one of the first competitions that will pop out in the new year in the current calendar is the AIME. The AIME will be held right at the start of February. Both the AIME 1 and 2 are in the early parts of February. So it's a good time for us to review the questions from the AIME, and I'll be looking at the problems from last year. Now, I realized I did not look at the questions yet in great detail, so this is a quasi-live solve. Right? I have glanced at it last year, but I never really worked them out in detail for some reason. So let's do it here together. Before we do that, just a quick note on the format. First of all, the AIME 1 and 2 are the same thing, just like the AIMC A and B papers are the same thing. It's a 3-hour and 15 problem paper, so you now have quite a healthy amount of time. Answers are integers from 000 to 999, and indeed, you will be asked, I believe, to bubble 3 digits like this. Now, if I am incorrect, please make sure that you read the answer sheet to know what exactly it says, but the last I recall, it would be like if your answer is 12, you're supposed to bubble in 0, 1, 2. Now, problems are worth 1 mark each. There's no marks for blanks, no marks for wrong answers, just very straightforward. But in effect, each question is kind of worth 10 marks if we are benchmarking it to the AMC. And the reason is because the AIME plus the AMC is what's used to determine qualification for the USAMO/USA GMO. How it's computed is just 10 times of your AIME score plus the AMC score, which effectively means that your AIME questions are each worth 10 marks. For instance, if your AIME score is, let's say, a 7, and your AMC 10 score, let's say 10A, you scored 121.5. Then 7 translates to 70, and this AIME plus AMC 10A combines to an index of 191.5. If you want to find the statistics on cutoffs, you can, but I would urge you not to be excessively concerned with the cutoffs, mainly because every combination of AMC and AIME will have a different cutoff. So AMC 10A plus AIME 1, AMC 10A plus AIME 2, AMC 10A plus, I forgot what I said earlier, but all the combinations have a different index cutoff. So if you felt the paper is harder, most likely the index cutoff is lower, and if you felt that you were very unfortunate, you got a hard AMC and the hard AIME, the cutoff will be a lot lower, assuming it's not just your own sentiment, but it's a general sentiment. The problems also are roughly in ascending order of difficulty, but they don't start off as easy as the AMC starts off. So we're going to look at the questions from 1 to 5 in this video, and you will see that right off the bat, question 1 would look like the difficulty of a late AMC 10 or 12 problem. So straight away, this is your easy question, quote unquote. Now, of course, if you put it into perspective, where the AMC gives you 3 minutes per question, if you do all of them, and for the AIME you have got a very healthy 12 minutes per question, then in a sense, this would be considered much easier than if you were to do this in an AMC setting. It also means we can take our time, so I'm going to take my time when explaining it. 5 men and 9 women stand equally spaced around a circle in random order. The probability that every man stands diametrically opposite a woman is m over n, where so the rest of it is just to make the answer an integer. Right, so from here to here, I can sort of ignore it. Okay, so I want to draw a diagram first. Let's draw a circle. And let's just indicate diametrically opposite using numbers, right? So let's say 1 and 1, 2 and 2, and so on. So 4, 5, 6, 7. Since they're 14, then I use these 2 sets of 1 to 7. Now, the probability that every man stands diametrically opposite a woman, when we're doing probability, we want to try to ask ourselves what matters and what doesn't matter. So, in a way, it doesn't matter how the men are arranged among themselves. It also doesn't matter how the women are arranged among themselves. It only matters how the men and women are placed, so we can sort of just use the letters M and W as if the men and women were all identical to each other. Now, secondly, we need to be clear. Every man stands diametrically opposite a woman. That does not mean that every woman is diametrically opposite a man, because there are more women than men in this circle. So, since there are fewer men, I'm going to focus on how to place the men. And when I want to place the men, I realize that if they are opposite a woman, it just means they are not opposite a man. So no men are opposite each other. Okay, so since this is what we want, we can just focus on placing 5 letter M's into this circle such that they are not opposite each other, i.e. they don't share the same number. So firstly, if we were to just talk about placing 5 M's, the number of ways to do this is just 14 choose 5. 5 factorial is 120, so that cancels nicely. I'll just leave it as 14 times 13 times 11. Since it's a probability, I'm going to do some fraction simplification later. So this is to place 5 M's. Now, how many of them would be non-opposite each other configurations? So no opposite M's. Well, essentially, you have to just choose which 5 numbers you want to take. So 7 choose 5. And then for each number, there are 2 positions that can be selected. So 7 choose 5, 7 times 6 divided by 2 is 21. I'm just going to leave it as this. So the probability, I think this is slightly easier to simplify because I can just 3 times 2 to the power of 4, which is 48, and then the denominator 13 times 11 is 143. So answer, to convert it to integer, we know that this is in simplest form, so 48 plus 143 is 191. Alright, question 2. I see a logarithm question. I often share with my students that it is very hard to set a hard logarithms question without mixing in some other stuff. This does not mix in any other stuff, so I don't think this is going to be very hard. For logarithm equations, you tend to be able to just simplify them directly because of the fact that your rules allow you to break things down very easily. So, for example, log of the square root is just half of the logarithm. And now, if I were to square both sides, it's fairly easy to see that log bn is equal to 4 or 0. Now, I doubt it will be 0 because if it's 0, then n is 1, and most likely that doesn't make sense for the question, but let's just look at the second equation to confirm that. So log bn can be broken up again into log bb plus log bn. Log bb is 1. So indeed, this confirms that 0 does not work, right? Because if you put 0 in here, you are going to end up with 0 equals to 1. So log bn is 4. and you have got 4b equals to 1 plus 4, 5. b is 5 over 4, and then for the purpose of the answer, I need to find n. n is just b to the power of 4. So a little bit of computation to get 625 over 256, and the answer for the sum of the top and bottom is 881. So indeed, not very difficult. It's just direct manipulations of logarithms. Now, question 3 is pretty interesting. It has one common idea. I put this in the thumbnail, so I've thought about it already. A plane contains 40 lines, no 2 of which are parallel. There are 3 points where 3 lines intersect, 4 points where exactly 4 intersect, 5 points where exactly 5 lines intersect, 6 points where exactly 6 lines intersect, and no points where more than 6 lines intersect. So it means that I'm looking at all the intersection points and asking how many lines go through them. So some of them will have 2, some will have 3, some will have 4, some have 5, some have 6, but there are no more than 6. Now this is a very classic double counting question. Now a double counting question means that you are counting the same thing in 2 different ways. Now a plane contains 40 lines, no 2 of which are parallel. That means that every pair of lines will intersect. So every pair of lines will intersect. Sorry, I think I need to adjust my screen a bit. Every pair of lines will intersect, and what that means is that in a normal situation where we don't have this huge bunch of intersections, every pair corresponds to an intersection point. So the number of pairs of lines is 40 choose 2. This is equal to 780. So if let's say that all of the intersection points were different, then you would have 780 points where exactly 2 lines intersect. Now certainly that's not the answer here, because there are all these points where many lines intersect. So if let's say that you look at points where 3 lines intersect, let's say something like this. Effectively, you have got line A, line B, and line C intersecting at the same place, which means that A and B, A and C, and B and C, all these 3 pairs of intersections are the same thing. So this one point basically corresponds to 3 pairs. And if let's say that you have now got 4 lines intersecting at a point, then there would be 4 choose 2 pairs, right? And so this is the idea. The idea is that if a point has a lot of lines going through it, many of the pairs will find their intersection there. So if you imagine that I do a roll call of these 40 lines, 2 at a time, and I ask, okay, line 1 and line 2, where's your intersection? Then they will say, here it is. Line 1 and line 3, where's your intersection? And they say, here it is. And then we will do this 780 times. In the 780 times, 3 times this point to be named, and 6 times this point to be named, and so on. So all I need to do is to just see how many pairs have already been satisfied by these points which have a ton of intersections. So the pairs accounted for is what I'll call it. You've got 3 times of 3, which is 3 choose 2, 4 times of the 4 choose 2, and then 5 and 6. So 3 times 3, 4 times 6, 5 times 10, 6 times 15. So 173 pairs have been accounted for by the points which we have mentioned so far. That means that the leftover pairs, which must have their own personal intersection, okay, so maybe I'll just say pairs accounted for by shared intersections. So your answer is just everything else, which is 607. Question 4. The sum of all positive integers m for which 13 factorial over m is a perfect square can be written in this form, where a, b, c, d, e, and f are positive integers. Find a plus b plus c plus d plus e plus f. Okay, so the first thing is that for this thing to be a perfect square, m is a factor of 13 factorial. Now, it's not just any factor of 13 factorial, but it is a factor. So I want to know what factors I can use. How many are there? Is it viable to list? Probably not. But one way or another, we have to factorize 13 factorial. Now, 13 factorial, incidentally, just 2, 3, 5, 7, 11, and 13 are the list of primes. So normally how I will do it is that for the primes that are more than half of this, we know they only appear once. So from 1 to 13, there's only 1 7, 1 11, and 1 13. For 5, there is 5 and 10, so it appears twice. For 3, there's 3, 6, 9, 12, but 9 has 1 extra because it's 3 squared. For 2, that's the one we need to calculate. There are 6 even numbers, and then you divide that by 2. 3 of them are multiples of 4. You divide that by 2 and round down. One of them is a multiple of 8, so the number of 2's is going to be 10. Of course, you could just write them all in a row and count it, but I prefer to do it this way. Okay, so this is 13 factorial's prime factorization. And so m has to divide away some things in order that the resulting prime factorization only has even exponents. How would that go? Well, I'll write it this way. 7, 11, and 13, there's only one of them, so you do need to get rid of them. Now, for 3, you have to get rid of at least one of it. But you could also get rid of any odd number of copies of 3. So you could divide off 3, you could divide off 3 cubed or 3 to the power of 5. Oh, okay. And then you realize that, oh, I can also do that for the 2's and 5's. Right? I can divide off nothing, which means just 1. But I can also divide all of this. So now m equals 2 is no longer accurate. It's the sum of m that I'm handling straight away. Each of these pluses represents kind of an OR condition. So it could be this times this times this times 3, or this times this times this times 3 cubed, and then this times this times this times 3 to the 5, and then I add them up. So that's why the plus is kind of an OR, since we're going to add it up later at the end. So same thing for the 2's, and then the same thing for 5, but 5 is just going to be 1 or 5 squared. Okay, so now here's the little bit of calculation we need to do. Remember that when I say the calculation, we just add this up and then after that we prime factorize it again. So we don't need to multiply them all together. That would be a lot more alarming. Okay, so 3 plus 27 plus 243, this is 273, which is 3 times 91, which is 3 times 7 times 13. Okay, this is 26, that's just 2 times 13. And then this one here is a little bit big. So in order to make my life easier, I'm going to factor it out by this way, algebraically, so that it is smaller numbers. 2 to the 6 is 64, so 3 times 7, 5 times 13. Let me highlight everything that I want so that I don't use something up twice. So this is the huge bunch of things, and since I just need a plus b plus c plus d plus e plus f, I'm basically counting primes. So I just go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And so the answer is 12, or 0, 1, 2, since we are in AIME I question territory. Okay, so lastly for this video, we'll look at question 5, a very short question, just 2 lines, and a square and a circle. What could possibly go wrong? We'll see. Right, so P is a point on the circumcircle of square ABCD. Okay, so I have a circle. Let's draw a circle first. All circles are similar to each other, so I can always draw a circle first. Square in the circle, I can always draw that. That's again all the same, just after symmetry. Well, not very squarish, but we can live with that. P is somewhere such that PA times PC is 56 and PB times PD is 90. I don't really know where that should go, but P is not involved in the end, so I can just put P anywhere I like. Now, take note that these are right angles because AC and BD are diameters. That seems like probably is going to be useful, but we will see in a little while. Okay, so I'll just maybe draw in the diameters as well. So I will also call the length of the square x. The diameter is going to be just x square root 2. And the area that we want is x squared. Okay, so let's see how we want to do this. I feel that there are enough pieces of information in here, definitely, that we can do quite a lot. I'll just call the side, not the sides, I'll call PA, PB, PC, and PD. I'll just call those A, B, C, and D. And I'll just gather some equations that we know. So we have got AC equals to 56. We have got BD equals to 90. That's given. We have now also got A squared plus C squared and B squared plus D squared are the same. And the same thing that they're equal to is the diameter squared, which is 2x squared. Okay, so this is the information that we have. If we look at this, it is, well, conceivable that this is going to be enough information algebraically to somehow squeeze out the value of x squared. But still, I think there is no harm in grabbing some other equations. So I'm going to grab another equation or two. I'm going to grab some equation using Ptolemy's. Now, Ptolemy's is probably useful because we have got so many repeated lengths, like just x everywhere and then x square root 2. So remember that Ptolemy says that for a cyclic quadrilateral, the product of one pair of opposite sides plus the product of the other pair of opposite sides is equal to the product of the diagonals. So for instance, if I use PABC, it tells me that PA times BC and then PB times AC is equal to PC times AB. So that conveniently allows me to cancel off the x, and so B root 2 equals to C minus A. And you can imagine that, okay, I'll change the order so that we know it's PACB is the quadrilateral. You can imagine that we can do this for any other combination as well. So PADB, if you were to preemptively realize that you can cancel off all the x's, you just get A root 2 plus B is equal to D, and then for PADC, it gives you A plus C is equal to D root 2, and then the other one is PBCD, that gives you B plus D equals to C root 2. Now here, with this many equations, it is quite hard to believe that we have not enough equations. Right now we have got a huge glut of things to use, and it is pretty much up to us how we want to go about finishing this problem. There are a bunch of choices, as we have said. So perhaps one thing that I might want to do is to just square some of these, because we've got A squared, B squared, C squared, D squared on top, as well as AC and BD. So I'll just square the last two equations maybe. I think this is very much up to us which one we want to do, but if I square them, I get something like this. If I expand it out, now 2AC and 2BD, I have got the values inside, so I can put them in. And A squared plus C squared and B squared plus D squared are 2x squared as well. So 2x squared plus 2 times of 56. So I can cancel off the 2. And then for this one, it will be 2x squared plus 2 times 90. I can cancel off the 2. And if I were to subtract off, here you get 34 equals to C squared minus D squared, which also means that it is equal to B squared minus A squared. I'm not trying to do this in the most efficient way here. I am just now saying that, okay, I've got this equation here. Am I able to combine it, the one on top, in some fashion? So c squared is d squared plus 34. It's not enough equation. So let me write it. I think I have too many equations there. In fact, it's scaring me a little bit. A squared plus 34 is b squared. D squared plus 34 is equal to c squared, and then I've also got AC is 56 and BD is equal to 90. To go in circles, I just want to now see if we can finish off and get x directly, or x squared directly. Am I missing something obvious? It probably am, right? Let me sit back for a second and look for some sort of ideas. Actually, I mean, I didn't use the other equation, right? I could definitely add and subtract some of these. So let me just think about that. Yeah, actually, maybe I should have done a different thing, right? I realized that this is one way that I could make the AC and BD appear. Another way I can make AC and BD appear is by multiplication. Because for some reason, I moved one of these over and I did not move one of them over. Maintain your symmetry, right? Keep things symmetric and you will not miss out things like this. So C minus A plus C, D minus B, and B plus D. By multiplying them, that's another way I can make AC and BD appear. So I'll do that instead. If I multiply them, I get C squared minus A squared equals 2BD, and D squared minus B squared is equal to 2AC. Now, I think this is a lot better, right? Because in this scenario, I end up with the equations on A and C twice instead of having equations on A and C, then equations on A and B, equations on C and D, and so on. So this is better. I think in fact just from AC equals to 56 and C squared minus A squared is 180. It's enough to solve as a quadratic, but I believe I can eyeball it and say that this tells me C is 14 and A is 4. Yeah, that seems to work. So if C is 14 and A is 4, then that allows me to get my 2x squared equals to 14 squared plus 4 squared is equal to 212. And so my answer is 106. Now, this is one of the things also about the AIME. As you can see, I am in no particular hurry. I just try to write a whole bunch of equations down, try something, it doesn't work, try something else again. You have the time. So one of the things that you want to get used to when you're switching from the AMC to the AIME is just that don't be afraid to make a big mess. Don't be afraid to try some things that don't work because you now can afford the time. In the AMC, the correct strategy is to skip it once you're stuck like this. For the AIME, the correct strategy, so just keep going at it. Don't panic and just keep in mind that you are not in a massive rush this time. So thanks everyone for watching. We'll be back with the next section of 5 questions in a little while. So see you then.